All right. So first, I'd like to thank the organizers for having me. It's a privilege to be here today and speak with you. This is actually my first time to Sweden and my very first Eurostrings, in fact. I'm an American, so let me move this over here. Um, Boundaries play a foundational role in physics. This is particularly the case in gravitational physics, where even the notion of conserved charge and mass requires a boundary. And of course, to have a microscopic interpretation of gravity, the time-length boundary of ADS is proven important in the context of holography. So today, what I'm going to be telling you about is recent developments on finite boundaries in gravity. And this is based on my work with my colleagues here. In particular, I'll be focusing on work with Avita Verheiden, Manas Visser, Eric Verlinde, Batul Banashemi, Ted Jacobson, Sergio Aguilar-Guettez, and also some recent work with my colleagues at King's, Damian Galente, and his truly remarkable PhD student, Chawarkorn Manarat. Okay. So let me give a kind of heuristic picture. Imagine you have some space-time manifold M with some finite boundary gamma. Here I'm imagining a Lorentzian spacetime such that gamma will be some finite time-like boundary. And by finite, I mean it has a finite size, so you really carve out a finite cavity or a world tube where inside and outside you can have dynamical spacetime. And these kind of finite boundaries have been used in gravitational physics before. It has a long history. So sometimes they're used in numerical relativity in practice. The stretched horizons of black hole, so black hole membranes, or stretched horizons of cosmological horizons. These are examples of finite time-like boundaries, and this is particularly useful in trying to do some modeling of astrophysical black holes. As you hear more about from me later, finite boundaries have been very useful in characterizing gravitational thermodynamics of black holes and de Sitter space. And of course, finite boundaries also have played a role in holography. They appear in holographic normalization. Brane worlds are example of finite boundaries. And TT bar or finite cutoff holography, the finite boundary plays a critical role. Okay. Now, so far, I've only told you part of the story. What I've said is incomplete in that you need to further specify the boundary conditions that your fields, in this case the metric, will obey at the boundary. And this is a choice that we make. And most often, the choices we use are, say, Dirichlet boundary conditions. This is where you fix the induced metric on your boundary. Or you can take Neumann boundary conditions, where you roughly fix the extrinsic curvature at the boundary. You could also use combinations thereof. These are known as Robin boundary conditions. But these are the kind of boundary conditions usually impose on the applications I was mentioning on the previous slide. Now, it turns out, and some of these results came out quite recently, that generically, these kind of boundary conditions are in fact ill-posed. What I mean by ill-posed, I'll say more in a later slide. But these proofs come from our friends in the mathematical relativity community. And it's in Euclidean context. This was shown by Anderson some years ago, and later reviewed again by Witten. In Lorentzian context, this was shown just a few years ago by Ann and Anderson. It turns out that it doesn't matter what cosmological constant you have in your background. So adding lambda doesn't ameliorate these issues of well-posedness. I should also say, though, that there are special cases where you do have that Dirichlet boundary conditions can be allowed. You can be well-posed, but you have to add in additional conditions, which I'll explain later what those are. But because of this, generically, these boundary conditions tend to be ill-posed, this led our colleagues in mathematical relativity to consider other types of boundary conditions. And one in particular is the conformal boundary conditions. And these are, you fix the conformal class of your metric induced at the boundary. So you fix your induced metric up to a conformal factor. And you also fix the trace of the extrinsic curvature. Okay. And these tend to be better behaved. So the point of this talk is I'm going to be explaining to you a little of this history and also the utility of adding finite boundaries, particularly in the context of Euclidean gravity and what they tell us about gravitational thermodynamics. So in the first chunk of the talk, I'm going to be talking about finite Dirichlet boundaries and the thermodynamics, particularly for de Sitter space. So we'll see how these can lead to important insights about the thermodynamics of the de Sitter static patch, defining ensembles. It'll also help us clarify this particular minus sign that appears in the first law of cosmological horizons. Then I'll switch gears and I'll talk about the thermodynamics you get from using conformal boundaries, finite conformal boundaries. And there's many interesting things. We'll see that you have thermally stable cosmological systems. It'll lead to new scalings for the entropy as you approach near extremality. And it turns out that the effective description of these near extremal black holes in the conformal ensemble is not actually characterized by JT gravity, but something else. And then if we have these boundaries that are dynamical, there's an effective description, at least in a particular case, which isn't described by a Schwarzian, but rather by a pair of Schwarzians. So that's essentially the outline of the talk. So that'll be our roadmap. Now, I should say I'm only covering a small sliver, a finite sliver of a lot of developments on this topic of finite boundaries. Here's kind of the various subfields that finite boundaries have appeared. Some results are relatively old and some are quite new. This is essentially a preemptive mea culpa for names that I will forget as I go along. But yes, there's been lots of work on this topic. Okay. So before I get to the thermodynamics of de Sitter, let me just first briefly summarize the status, what happens for black hole thermodynamics. And luckily, Samir gave an excellent review talk, so I can rip through this. So Bekenstein first proposed that black holes have an entropy proportional to the area of their event horizon. Hawking found that they actually radiate at a temperature proportional to their surface gravity. And this here, I just write down in terms of the Schwarzschild black hole in 4D. And what this tells us is that black holes are genuine thermal systems. The laws of black hole mechanics can be identified with the laws of black hole thermodynamics, in which the internal energy of the system is identified with the conserved ADM mass of your system. And you can derive this using Gibbons-Hawking prescription with using a Euclidean path integral derivation. Basically what they showed was that you define a canonical partition function into leading order in some stationary phase approximation. It's given in terms of some on-shell Euclidean action, which you can compute. And from there, using basic stat-mech principles, you can then write down your various thermodynamic quantities. Now, a peculiar thing about the Schwarzschild black hole is that it actually has negative heat capacity, which means it's thermally unstable. This is not so surprising. You put this black hole, there's some infinite space, it's radiating, and so it's not going to be in thermal equilibrium. But what this means is that since it has negative heat capacity, this comes from elementary stat-mech, means that the canonical ensemble is actually ill-defined. And this was even noted by Hawking long ago. And so, one suggestion is you should appeal to the microcanonical ensemble where you fix the energy of your system. And this has also been, considered by Brown and York and others since then. Now, another approach championed by York was to put a black hole in a box. So the idea here is let's take the Schwarzschild black hole of some mass m, and we'll put it inside of some finite-sized box of some fixed radius. So on the right-hand side here, imagine this is my Euclidean cigar, which now I've put some finite boundary gamma there. Okay. Now, what York did is he assumed Dirichlet boundary conditions such that the metric induced on the boundary is fixed. And fixing these kind of boundary conditions, they also fix your thermodynamic data, which then specify your thermal ensemble. So in particular, the canonical ensemble is you fix the temperature relative to this finite boundary. So you're fixing the proper periodicity associated with that boundary, which is not the Hawking temperature, but rather what's known as the Tolman temperature, which is essentially equivalent to the Hawking temperature up to this redshift factor, this root here. Now, in the limit that I take this finite boundary and I send it all the way back to infinity, such that I have the entire Euclidean cigar, you'll notice that the Hawking temperature just becomes the Tolman temperature. You then just apply basic Gibbons-Hawking prescription to write down your essential thermodynamic quantities. And what you find is that the total internal energy of the system is given by the Brown-York energy, which takes this form here. This is some conserved quasi-local charge. Notice that in the limit that r goes to infinity, this just recovers the ADM mass of the black hole. You find that the entropy is the same. It's still just area of the horizon of the black hole. Notably, though, what what York showed was that these systems have positive heat capacity, at least for large enough black holes relative to the size of your boundary. And perhaps this isn't so surprising because this is the same thing that happens when you put black holes in ADS. You can find systems where you have positive heat capacity. What this means is that the canonical ensemble is well defined in this context. And what's more is that you can take these thermodynamic quantities, you can derive a quasi-local first law, where now EBY, this Brown-York energy, appears on this side here, but you also have a new term, this kind of pressure area-like work term as well. Okay, so now black holes aren't the only systems that have horizons. Particularly, de Sitter space also has a horizon. So here's a picture of de Sitter space, the Penrose diagram. This shaded blue region is the static patch covered by these coordinates here. And to observers, static patch observers stuck in the static patch, in our case, Chawakorn, he would encounter a horizon at r equals L, known as the cosmological horizon. Okay. Now, since it has a horizon, what this suggests is that there is some, you might expect that there's some thermal description of the de Sitter static patch. And indeed, Gibbons and Hawking showed that the area of the horizon is related to the entropy of the system, and that also has a temperature proportional to the surface gravity. And they also derived this using Euclidean path number derivation, where they found to leading order, the on-shell action is proportional to the Gibbons-Hawking entropy, and that the energy is vanishing. Now, to my colleagues and I, we thought this derivation was a bit cavalier, because when you take the static patch, when you Wick rotate it, you find that the system is just a sphere, which has no boundary. So there is no location for you to define fix a conserved charge or fix other thermodynamic data to define thermal ensembles. Now, even ignoring this puzzle for us, de Sitter thermodynamics is also curious in that it has this minus sign that appears in the first law of cosmological horizons. So here on this side, on the right-hand side, this is a mechanical statement. So you add in some killing matter, say, and you pick up, this is the response to your horizon, to your cosmological horizon. And this is why we often say you throw something into the static patch, it reduces the entropy of empty de Sitter. And it's because of this minus sign. Now, if we want to understand this as an ordinary first law, we should also have an interpretation of this minus sign. And so that's another puzzling thing about de Sitter thermo. Okay, now both of these puzzles for us, you can clarify if you put de Sitter in a box. So what we do is, this is the setup. You take a finite boundary. We're going to assume Dirichlet boundaries. You put it inside of this de Sitter static patch in this way. This divides the static patch into two regions. One is this bluish purplish region here between the pole at r equals 0 and the screen. This is known as the pole patch. The complementary region is between the screen and the cosmological horizon. This is known as the cosmic patch. Now, an important limit that we can take is you can have the full static patch limit. So if you're confined to the pole patch, so you don't see the cosmological horizon, you can take the limit that r goes all the way to the cosmological horizon. And that would then fill, and you'd have the entire static patch. You can also go the other direction, where if you're confined to the cosmic patch, you take the screen and you send it all the way to the pole, and that would also give you the full static patch region. Now, just in the same way that York did, we can consider the canonical ensemble. So these boundary conditions they define for us are thermal ensembles. And the canonical ensemble, just as for black holes, is you fix the Tolman temperature of the system, and you also fix the size of the system. From there, you can just then apply basic stat mech principles, and you will find that the total energy of the system is given by EBY, the quasi-local Brown-York energy, and the entropy is just that of the Gibbons-Hawking entropy. And I should also comment, this is the same kind of setup that one uses when trying to find a macroscopic interpretation of the de Sitter static patch using TT bar or TT bar plus lambda-like formalisms. Okay, what's more is you can derive a quasi-local first law. We did this using some covariant phase space methods. This E sub m here, this is just the change of the killing matter energy that you put inside of your static patch. And this limit I was mentioning, let's suppose you're in the cosmic patch and you take the limit such that you go all the way to the pole, to the full static patch limit. Then as r goes to 0, your Brown-York energy goes to 0, the Tolman temperature goes to the Gibbons-Hawking temperature, and you simply recover the historic first law of cosmological horizons with its minus sign. And prior to our work, what was often assumed was that this, the interpretation was that this E sub m should be viewed as the total internal energy of the system. And then what's more is that you should view this not as a first law with respect to the static patch, but actually beyond the horizon. So this was an interpretation by Strominger, Volovich, and Sprodlin. But by our calculation, what you see is that what you should view is that the Brown-York energy, just like in black holes, is the total energy of the system. So you should not view EM as the total energy of the system, and that the minus sign does appear, but it's just at this static patch limit. And you should view this first law as really being a first law inside of the static patch. So it's one that a static patch observer would see. Okay, I'll skip this comment actually. I can come back later. Okay, so that's kind of the status about Dirichlet boundaries and what they can do for us regarding thermodynamics of de Sitter. So let me move on and talk about other types of boundary conditions. You might ask, okay, why should I consider other boundary conditions? Well, first, what I didn't explain yet is that actually with these Dirichlet boundaries, there are no cosmic patches, so no systems that have cosmological horizons that are thermodynamically stable. You always compute having a negative heat capacity. So that means we're back at the same problem that York was first trying to overcome, and that the canonical ensemble is not well defined in this case. Now, aside from that, just generically, Dirichlet boundary conditions in GR are generically opposed. And so what that means is, so for example, in the Euclidean context, what you find is that Dirichlet boundary conditions are not what we say are elliptic. And what that means is that it doesn't lead to a sensible perturbation theory that you want to have if you're trying to do some sort of semi-classical gravity and describing gravitational thermo. This was proven by Anderson and then again later investigated by Witten. There's also, in the Lorentzian context, proven just a few years ago, that generic Dirichlet data will not satisfy existence or uniqueness conditions for having a well-posed initial boundary value problem. So basically, for generic Dirichlet data, they will not satisfy the Hamiltonian constraint projected onto the boundary. Now, there are existence and uniqueness issues also in the Euclidean case, which was also proven by Anderson as well. Now, there are exceptions also recognized by Anderson and Witten and my colleagues at King's. And essentially, in addition to Dirichlet boundary conditions, if you impose having the extrinsic curvature or the Brown-York stress tensor having a definite sign and having the same sign as the induced metric, then you can find situations where the boundary conditions will be well posed. But generically, that is not the case. So this led people to investigate other types of boundary conditions. In particular, you had conformal boundary conditions where you fix the conformal class and you fix the trace of extrinsic curvature. What this means is that now what K will do is it will tell you basically the size of the system. It also tells you kind of where the position of the boundary will be in your space, whereas the shape of the boundary will be governed by the conformal class, which is fixed, but it'll have some dynamics because you have this free conformal factor that you have not fixed. Now, the first immediate thing that happens at the level of the action is when you change these boundary conditions, you need a new boundary term to have a well-posed variational problem. So it's no longer the Gibbons-Hawking-York boundary term, but rather it's this kind of rescaled version of the Gibbons-Hawking boundary term. And you also find, instead of the Brown-York quasi-local stress tensor, kind of the analog with this conformal boundary conditions. You notice that it's traceless, and if you're at fixed K, it is also conformally or covariantly conserved. And even though this extra factor here might seem innocuous, we'll see it has profound implications later. Just a couple more comments is that these kind of boundary conditions, they were proposed originally by York back in the 70s, but for space-like surfaces when he was trying to understand the Hamiltonian evolution in GR. These are, in fact, the same boundary conditions that we use in ADS CFT, so we're actually quite familiar with them. One thing we often forget is the extrinsic curvature of the infinite time-like conformal boundary of ADS is actually fixed. So when I say putting things in a box from now on, it basically we're putting things into an ADS box. Interestingly, using conformal boundary conditions appeared in the fluid gravity correspondence some years ago. This was shown that when they're trying to find solutions to, when you're looking at a time-like boundary very, very close to the horizon of black holes or cosmological horizons, there was an obstruction actually with Dirichlet boundary conditions, but they found that this obstruction went away if you included conformal boundaries. They're well posed, they're proven to be well posed, by Anderson and Witten. And about a year ago, it was found that there is a one-parameter extension leading to some kind of generalized conformal boundary conditions by our colleagues Liu, Santos, and Wiseman. These were also proven to be well posed in the Euclidean context. Okay, so let me just have a one-slide summary of the status of well-posedness of these boundaries in Lorentzian GR. So just very recently, a few months ago, it was proven by Andy and Anderson that they satisfy a linearized proof for any Einstein background. But it turns out, initial boundary value problem, I should say. It turns out that nonetheless, for spherical boundaries, you have these growing modes at large angular momentum. And these growing modes were used by Liu, Santos, Wiseman, and Real to show that there is actually a violation of the so-called Hadamard criterion, which basically just says if you perturb your initial data, you can have wildly different solutions. Now, I won't go into more details about what's going on with the well-posedness of the Lorentzian context. There is a wonderful talk by my colleague Damian. It's on YouTube, so when you download my slides, you can just click on this link. But all this is to say is that there are still some open questions about the status of conformal boundaries and their stability. And so, interesting question is, why do these conformal boundaries have growing modes? And this is work in progress with my colleagues at King's, Dio, Damian Chawakorn, and a very good postdoc who's also here today, Sylvia Georgescu. She's here a week, so if you also have questions, you can talk to her. Okay, so back to Euclidean gravity with conformal boundaries. So we can now just use the usual Gibbons-Hawking prescription. We have the canonical partition function expressed in a stationary phase approximation in terms of just this on-shell action. The boundary conditions, just like in the Dirichlet case, our boundary conditions will give us a new type of thermal ensemble. For the canonical ensemble, so the conformal canonical ensemble, what we fix is not the Tolman temperature, but we fix the so-called conformal temperature. This is essentially a conformally invariant quantity that you can construct from your Tolman temperature and your radius of your system. You also fix the trace of the extrinsic curvature. You then apply basic stat mech principles, and you will find the internal energy, the entropy, and so forth just by appropriate beta derivatives of your canonical partition function. And as an explicit example, take the Schwarzschild black hole in any dimension, but you can. And what you find is that the energy is given by the conserved quasi-local Brown-York energy, assuming conformal boundary conditions. This was a charge that was originally derived by Odak and Speziale. The entropy is just the area of the black hole horizon. And you can also write down quasi-local first laws like this, where you have the conformal temperature, this is your quasi-local energy, but you also get a term that goes like this, where this V here is the volume, or it's proportional to the volume of your spatial boundary. Okay. Now, there are loads of interesting things that come out of working with conformal boundaries. The first thing is that you actually have stable cosmic patches. So this is in even empty de Sitter space. You can find a region in your parameter space of your thermodynamic data that you'll find, you compute a positive heat capacity. This is in stark contrast to what we saw for the Dirichlet case. So this means that you can, you have well-defined canonical ensembles that you can explore with conformal boundary conditions. What's more is that if you take the high temperature limit for spherical black holes and also empty de Sitter, you'll see that the thermal entropy just goes, it scales in this way here with the conformal temperature. And this just is precisely the scaling of a thermal CFT in one dimension less than your bulk gravity theory. So this is, and this function, this NDOF here, is suggestively written to indicate that perhaps this gives you some kind of generalized notion of some central charge of whatever your putative dual of your finite system would be. Let's take, for example, the bottom line here. This is if you had a negative cosmological constant. One thing is if you take the quantity k times L, where L is the ADS length scale, and you go to infinity, you'll just recover what the flat space analog of it is. But what's more is let's suppose we take KL and send it to this value d minus 1, what you find, so this is taking the conformal boundary, the finite conformal boundary, and sending it to the infinite conformal boundary of ADS. And what this gives you is you'll recover the central charge of your CFT that's living on the boundary. And so particularly in the ADS3 case, if you take KL to 3, you would recover the Brown-Hanot central charge. And so this shows that as you push the boundary in, you get these, this quantifies corrections to your generalized central charge of your system. So this is, quite tantalizing, and then it suggests that this finite region with these conformal boundaries is described by a local quantum field theory. Essentially, what you've done is as you push in the boundary, your conformal factor has dynamics, and it couples to bulk gravitational degrees of freedom. And you could ask, what are particular proposals of this dual theory? And just a few weeks ago, Edgar Shigulian and his student, they were exploring this in the context of ADS3. Okay. Now, what's more is if you take a charged black hole and you put it in one of these finite ADS boxes, you'll be led to other temperature scalings of the entropy as you approach low temperatures. And this is because when you have these conformal boundary conditions, basically near extremality is found by a pair of limits, by some double-scaled limit. So you take your conformal temperature and you send it to infinity. But you also have this quantity kq, where q is the fixed charge of your black hole. You let it go to 1, and you let the quantity beta tilde times kq minus 1 be some constant. And this will lead to a family of various scalings you could get. So here's a plot that we computed. This green region is when you go near extremality. And what you find is that in this region, that at very low temperatures, you'll see that the entropy, so you take the entropy minus the extremal entropy, and it scales as linear with the conformal temperature. This is precisely the same kind of thing that Samir was looking at in the previous talk. But also as you increase in temperature, you'll see that it scales like quadratic in the conformal temperature. And in this whitish region here, you're approaching higher temperatures. So if you're, say, the Nordstrom black hole, in the conformal ensemble, what you have is that at high temperatures, it will behave, the entropy will scale like a thermal CFT in 1 dimension less than your bulk theory, so say a CFTD minus 1. But then as you get really close, it scales like a near CFT1. Okay. Now you can ask, okay, what is the effective description describing these near extremal black holes in the conformal canonical ensemble? So just very briefly, when you have an extremal black hole, say the extremal horizon Nordstrom, the near horizon geometry goes like ADS2 across S2. You can also have the same thing, or roughly similar thing, when you have de Sitter black holes. So you take a black hole, even uncharged, put it in the de Sitter static patch. There's a limit, known as the Naria limit, where the black hole horizon matches or coincides with the cosmological horizon. And in that geometry, the near horizon geometry looks like DS2 cross S2. And by now, it's essentially common lore that deviations away from extremality is captured effectively by a 2D dilaton theory of gravity, either ADS2 JT or de Sitter 2 JT gravity. And you can put in, finite Dirichlet boundaries, for example, to explore the quasi-local thermodynamics of these systems. And that was one of the things that we looked at. Now, we can play the same game, but let's investigate the conformal thermodynamics of these near extremal black holes. And so what you do is you perform a spherical dimensional reduction of your full theory. So that includes the boundary conditions as well. And these are what the boundary conditions would look like in this blue box. Phi here is just the dilaton, alpha is just some constant. So this is just the dimensionally reduced conformal boundary conditions from the higher dimensional GR perspective. You also get the action that takes this form here, where it goes, this U phi is the dilaton potential, but you also have this term here, which is the analog of the Gibbons-Hawking-York boundary term, which is the right term that you need in order to have a well-posed variational problem, assuming these boundary conditions, but it's also just the dimension-reduced Gibbons-Hawking boundary term for conformal boundary conditions. And the main takeaway of this slide is that if you want to describe the thermodynamics of the near extremal system that I was looking on the previous slide, the linear potential, so if you go linear in phi, is not sufficient, and that would be JT. In fact, the linear potential is it only describes the extremal black hole physics, except for maybe a constant shift in your energy. So actually to recover the near extremal black hole thermodynamics in the conformal ensemble that I was looking at in the previous slide, you need to go to at least a quadratic order in your dilaton potential. Okay. So far in this whole talk, I've only just been thinking about static boundaries. So I have, fixed the conformal class, but I'm assuming that the conformal factor is static. One thing you can do is, since we have conformal boundary conditions, you can allow this boundary to become dynamical. And so let's consider the case where we have spherically symmetric spacetimes where we allow this conformal factor to be non-static. What you find is that when you impose conformal boundary conditions, this will be led to a complicated second-order differential equation which characterize the dynamics of your conformal factor. And to kind of grapple or make this tractable, what you can do is let's consider the simplifying case if you take a ADS-D system. And then we're going to take our finite conformal boundary and send it very, very close to the infinite conformal boundary. And this is deviations away from that boundary is characterized by this change in k here. So this is what the value of k would be at the actual boundary. And to leading order in delta k, such that we're now just inside of the ADS boundary, this is what the differential equation would be governing the dynamics of omega would look like. It's a bit simpler to look at, and particularly it simplifies in the case where you have ADS3 in the bulk, because then you see that omega just obeys some one-dimensional Liouville equation. You can ask, okay, what is the effective action of this 1D Liouville equation? And essentially, if you follow the same procedure that you would have done for, say, deriving the Schwarzian description of ADS JT gravity, what you find is that the boundary action that governs this dynamics is given by the following. This first term is just the usual Schwarzian that we have for parameterizations, this T of U parameterizations of as you put your boundary inside of your space. But then you also have this additional Schwarzian where gamma here is related to this omega in this way. And what's interesting is you have this relative minus sign between the two Schwarzians. And this is the same thing that you see when you couple a Schwarzian to 1D conformal quantum gravity. This was first observed by my colleagues here. And this is basically just, again, showing that as you push the boundary in, you have that the conformal factor, some boundary dynamics, is coupling to your bulk degrees of freedom. Okay. That's at least in this particular case here. All right. Oh, let me go back. Very good. Okay. So just to briefly summarize, so I hope I've conveyed that finite boundaries are very interesting in the context of gravity. They're applied in various contexts. There's also been some synergy between the mathematical relativity communities and high energy physics. In particular, conformal boundaries and finite conformal boundaries invite new kinds of physics, and they really help us hone in and try to understand microscopically a finite piece of space-time. There are loads of future directions one can go. We haven't really explored the microscopics of these various theories, even in the low dimensions. So you can ask, is there a TT bar-like description? There's been some work on this already, some pretty recently. I've only talked about the tree-level thermodynamics of the system for these exchangeable black holes. So you can ask, of course, what happens if you add one-loop quantum corrections. And there's still some outstanding questions regarding the well-posedness and stability of conformal boundaries, particularly in the Lorentzian context. But with that, thank you again. I'll take any questions.
We have plenty of time for questions.
So how does this change the story Samir was just telling us for the Reisner-Nordstrom black hole?
So we don't know the answer yet, but I would say because you have this linear order temperature correction for near extremal black holes, it seems like the story would be probably similar. But the problem is our low D theory is not just this Schwarzian action anymore. So we have this coupling that happens. Now, the other thing is, if you want to ask this question looking at one-loop corrections as well, you have to also we have to include all sorts of geometries in our Euclidean path integral. We have to sum over all various saddles. And that means we also have to include these dynamical boundaries, which we don't know how to do yet. But that would be the first thing. So there should be a similar effect as what Samir is saying. I don't think we're saying anything surprising there.
You mentioned the one parameter extension of these conformal boundary conditions. Can you just
Yeah. So basically, there's this. If you write the trace of, it's the trace of your induced metric raised to some power. It could be a rational number times the trace of the extrinsic curvature. That basically modifies. That's like it replaces one of your just fixing the trace of the extrinsic curvature. And fixing that, various powers of p will lead you to different types of conformal boundary conditions. And there's certain limits of p that you will recover, the usual ones that Anderson had first was looking at. And then in some other limits, you will actually recover the Dirichlet boundary conditions as well.
And it would still ensure the well-positiveness?
Yep. Unless you go to I think it's p minus infinity or p plus infinity where it becomes Dirichlet. But away from there, it's well posed in the Euclidean sense.
Any further question? If not, let's thank our speaker again.
Thanks.